Welcome. Thank you all for joining this webinar about the MIPI I3C serial communication bus. My name is Clemens Valens. I work for Elektor, and I will be assisting our guest presenters Tim McKee, Michel Scalatella, and Eudel Zoudou-Teferi from MIPI. Tim McKee works at Intel, if I'm not mistaken, and he is chairman of the MIPI I3C working group that develops and maintains the I3C interface specifications. Hello, Tim, nice to meet you. How are you doing?
Hello, Clemens. Nice to have a chance to come here and speak to you all. Thanks for having us.
Thank you. We also have Michel Scalatella. He is currently an IoT technical consultant for the MIPI Alliance after spending many years at ST Microelectronics within the microcontroller and ICs division. So hello, Michel. How are things today in Milan?
Hi, Clemens. Yeah, fine, great. Really happy to be on this webinar and to explain this technology.
Yes, nice to have you. Our third guest is Eudel Zoudou-Teferi from ST Microelectronics also, and he is currently the vice chair of the MIPI I3C Basic ad hoc working group. Hi, Eudel. Nice to meet you. How are you doing?
Hello, Clemens. Hello, everyone. I think it's really good to be here, and thanks everyone for joining us on this I3C presentation.
Yes, you will assist us for the Q&A, right?
Yes, I'll be assisting on the Q&A.
Okay. Thank you. Today we will present the I3C interface from the MIPI Alliance. I3C is a scalable general purpose two-wire serial communication bus for connecting peripherals to microprocessors and microcontrollers. I3C is designed as the successor to the popular I2C bus that most of us know quite well. There will be a lot of information, but don't worry if you can't follow along with the presentation, because this webinar is being recorded and will be available afterwards on the Elektor TV channel for replay. As usual, at the end of the webinar, you can ask questions, and you do this by typing them into the Q&A chat box, which is on my computer down there. Having that said, let's get started, and I will pull up the presentation.
I've got control, so I'll get us started. Thank you, Clemens. Welcome everybody. I wanted to start off real quick, just talk about the MIPI Alliance. So back in 2003, MIPI was formed and went after standardizing camera and display interfaces. Now, we fast forward to 2023, the MIPI Alliance has developed more than 50 specifications, all sorts of range of interfaces, and has really broadened their reach. Today's MIPI ecosystems, over 375 members, spanning across multiple countries and many different industries, from semiconductors to software, to test labs, IP and VIP providers all over the place. So MIPI has grown since its initial inception, going after that mobile market. So beyond mobile, as I was saying, MIPI has really branched out. On the left side, you can see this mobile system diagram highlighting all of the different technologies that MIPI has been able to produce, from display, Unipro, DigiRF, debug, all sorts of different interfaces spanning the mobile system, but also outside of that, getting into IoT, industry, automotive. Those 50 specifications that MIPI has produced has really broadened that reach, right? But today, as you all know, we are here to talk about I3C and I3C Basic. So if you're familiar with I2C, this may be somewhat familiar to you. I3C simply stands for Improved Inter-Integrated Circuit, and it is based off of the I2C interface. So let's dive in. What is MIPI I3C interface? Well, the MIPI I3C interface, it's built to be a smarter interface with more capabilities for sensing and control. As everybody knows, the market for sensors has grown. There's sensors in every device that we use, and with those sensors comes a lot of information, and that was one of the main reasons that the I3C bus was built, was to be able to interface with those sensors and communicate. But as I had mentioned earlier, I3C has really grown into the camera and display, high performance compute, and even into the automotive range. So I3C is now built as a scalable and cost-effective interface, reduced pin count for low power, high-speed communication to compete with similar technologies like I2C, SPI, and UART. And we did build this in with backwards compatibility in mind, and so there is a level of compatibility built in I3C with the I2C interface, and so that you are able to have a mixed bus situation where you have both I3C and I2C devices on the same bus, which we'll get into more detail on that later. So what has I3C brought to us? Well, previously, if you looked at kind of a SoC die design, it was pretty complex. You had an I2C controller with its 2 lines and its independent interrupt lines. On top of that, you had to have an interrupt controller, a SPI controller, UART, a lot of different pins and a lot of different traces on your design. Well, with I3C as an alternative, and it's multi-tap bus style, now those 2 wires that are produced from the I3C technology can actually connect all of those devices on the bus instead of needing to implement multiple technologies in order to handle all of the different sensors and components on your SoC. So with I3C, this 2-wire interface brings much faster, up to 33 times faster, and reduced energy and a much cleaner design. As we know, more pins and more traces can cause more cost and complexity to any design. Now, we've mentioned 2 different flavors of I3C. There's the I3C specification, also sometimes referred to as the I3C full specification, and then we have the I3C basic specification. Starting with the full I3C specification, this one is freely available to MIPI members, and it has 2A IP protection. This is everything that we've designed and delivered for the I3C technology. This was the original release was created back in 2016. Our latest release, the I3C version 1.1.1, was released back in 2021. Now, through the development of this technology and this ecosystem, we developed the I3C basic specification. This was created as a publicly available FRAND-Z specification with a reduced feature set. So 6 of the 22 features that are in the full specification are not included in I3C Basic. I3C Basic is what we consider the kind of the broken down, the most basic, I guess, version of the I3C specification. So between those 2, there are some options. We've seen that I3C Basic has been a great addition to our IP, so that to broaden our reach and get this I3C technology out there into other working groups and out there across technology. So getting into a little bit more of the detail about how I3C works and its electrical features, as we've mentioned, it's a 2-wire bus, a 2-wire interface with an SDA, which is our data line, and an SCL, which is our clock line. And as you can see at the top there, our data is valid in between the transitions. And so we have a variable voltage range ranging from 1.2 volts to 3.3. And the current drive on a 50 picofarad bus load of around 4 milliamps. And so as you can see on these figures here on the right side of this slide, the communication style for I3C is well defined. We have start conditions and stop conditions, as well as a repeated start condition to have continued communication without having to go through that stop to increase the efficiency. We also have multiple data rates cooked into I3C. The standard data rate is built for up to 11.1 megabytes per second, but there are also higher data rates available. These are some of the features that I3C enables, and so there's multiple data rates that you can implement that will increase that that throughput. Okay, so with these two wires, the drive type is variable as well. So the SDA is driven by the controller or target. So the data comes from either side, controller or target. Just to take a step back real quick, the controller and the target are two primary roles, right? Our controller is kind of the manager of the bus. A target would be something like a sensor that it is trying to communicate with. So both can drive data. And that bus will dynamically switch between open drain, push-pull, high Z, and high keeper, all in order to keep the efficiency and power in check. Now the SCL, on the other hand, is driven by the controller, and always with a little asterisk in push-pull mode. There are a few scenarios that we've listed down at the bottom of this slide in which the SCL can be in high keeper or in some other mode, but as a general guidance, the SCL is always in that push-pull mode. So what does this do for us? Well, this creates efficient bus transactions, minimizing energy, reducing the number of transactions, and using push-pull mode whenever possible. So talking about the roles and configurations, I mentioned the primary or the controller and the target. Those are our main roles within the I3C technology. For a primary controller, there's only one per bus. For targets, there can be many, and within a target, there can actually be virtual targets. So if you have a device that you want to separate into basically different devices, that is built into our spec with our virtual targets. There's also the ability to add a secondary controller. It could be a specialized controller that is designed for special conditions, all sorts of different things. And there is a handoff procedure that we have designed to be able to hand off the controller role from the primary controller to the secondary controller. Of course, I2C targets. There are many sensors out there that still operate on I2C, and so with the backwards compatibility that has been built into the specification, we can still have I2C targets on the bus and create that mixed bus situation. And then finally, there's other special devices, bridging, routing devices, other pieces in order to either segment the bus or to allow different features. Okay, so what's the controller's duty? As I mentioned, there's only one, and mostly it's there to generate the SCL and then manage the bus, assign dynamic addresses, enter into HDR modes, deal with in-band interrupts and hot joins. It is really the center point of our I3C bus. And then at the bottom here, we talk a little bit more about the routing devices. One of the bridging and router devices, what can be done is you can segment the bus. So for instance, if you had a segment of I2C sensors, you could put that on a segmented part of the bus to keep that isolated through one of our special devices. So a lot more detail. There's obviously plenty to read in the specification on all of these. A lot of details and work has gone into this specification. So moving on. So we mentioned a little bit earlier these higher data rate modes. The HDR, the high data rate, BT, which stands for bulk transfer, DDR, which is dual data rate, and multi-lane. All of these are built to increase the throughput of I3C. So quick brief summary on double data rate. The SDA shifts on each SCL transition, so we've kind of double the data there. It's a block-oriented formatting. With multiple lanes instead of the standard 2-wire bus with a single SDA and SCL, we can now add multiple SDA lines. And so you can have either 2 or 4 SDA lines, and this is also available, the multi-lanes is available to combine with our HDR, DDR, or TSP encodings, which TSP is another form of our HDR. Finally, there's the next one is the bulk transport mode. Bulk transport's actually a part of the basic specification. It supports dual and quad SDA lanes, and with bulk transfer, we're working in the 32-bit data blocks. And so what this allows us to get a lot more data through in a shorter period of time. And we have dedicated commands for all of this. We have a command structure called our common command codes, or CCCs, and these are all built around these features to enable ease of entering and exiting and so forth. The last of the HDR modes is the ternary, the TSP or TSL. And with ternary, the SDA becomes a 2-wire signal. And basically, as you can see here, we have the 3 combinations on the right side with the SDA low, SCL triangling high to low, and then the various other combinations. Those 3 states are possible, and this is once again more of a block-oriented transport. But there are two flavors of it. The ternary symbol pure bus, which does not allow any I2C devices, and then there's the ternary symbol legacy inclusive bus, which would allow and is built to allow I2C and that mixed bus. And just a note here, those ternary modes are part of our full specification and not available in the I3C basic specification. So what does all of this, all of these extra features, all of this technology really bring to us with I3C? Well, first and foremost, we get a much higher bit rate than your classic I2C. In this top left graph, you can see I2C all on the right with the raw and effective bit rates very low, whereas as you look on the left side with our HDR and even the SDR, the standard data rate modes for I3C, we can get a much higher bit rate, and on the bottom you can see jumping that, implementing the multi-lane, we can even increase that to higher levels, upwards of nearly 100 megabytes per second, which would be, as you can see, with the quad lane TSL. So this I3C technology gives us much better throughput than we saw in the legacy I2C. On top of that, we also looked to be more efficient. So the bus performance for 1 kilobyte transfers, once again, in these graphs, you can see I2C, the legacy I2C on the right side, with the average up near, what is that, 8 microjoules. Whereas when you look over even at a standard SDR I3C, we're looking under 2 microjoules for a 1 kilobyte transfer. So a huge increase in energy reduction, 4.3 times lower, in fact, for the standard data rate, and higher reductions for our HDR modes. And then, of course, the transfer time has decreased due to the faster operation and throughput. So with I3C, not only are we getting better throughput, but we're doing it with better energy savings as well. So it's why we love this technology, and we're seeing it grow across the industry. So with that, I'm going to go ahead and pass it over to Michele to talk about the transactions, common command codes, and some of the special features that are included in I3C. Go ahead and take it away, Michele.
Thank you, Tim. So after this nice introduction, I'll try to get a little bit more into the, let's say, nitty-gritty, some details, just to give you a better understanding from an engineering point of view. So the first thing is, as Tim said, he showed the transaction that is a bus transaction which borrows a lot from the I2C. If you're familiar with I2C, you recognize the start-stop conditions and the data line moving when the clock is high. But when you look with the magnifying lens, let's say, actually things look a bit different. So here is the typical start of a transaction. On the top, you have the SDA line. On the bottom, the clock line. Basically, usually the transaction starts from the controller issuing a reserved address at 7E. This is a reserved broadcast address by I3C. It's actually an address that cannot be, it's forbidden in I2C, so there is no collision there. And the transaction starts off in open drain. So as Tim said, only the SDA line, it really switches between open drain and push-pull, while the SCL is driven by the controller. You will notice, that the rising edge is kind of slow because in open drain, this depends on the capacity on the bus, on the pull-up resistor. And then you clock, here the rate is actually lower because you need to take into account of the slow rise time. And effectively, it's in the range of 4 megahertz. You can achieve so roughly 4 megabits in this stage. At the end, there is the read-write bit. It's always a write. It's a negated write. And then what happens if there is at least one I3C device on the bus, it needs to acknowledge. If a device sees this broadcast address, you will need to do an acknowledge. The acknowledge is also in open drain. So it's enough that just one device is pulled down the line. At this point, the controller knows that there is at least one I3C, and he can talk I3C, let's say, in full speed mode. So what happens, he can do a repeated start. At this point, the line is switched in push-pull. Now you see that it's becoming blue. And you can see it can go much faster. It goes at full speed at 12.5 megahertz. So it's and notice that at the end of the second byte, it goes again back to push-pull to see if there is an acknowledge. And then eventually, if it continues, there is no more push-pull generally. And this is true 99%. There are special cases which it is not true, like in dynamic addressing assignment. You may also notice that the clock on the first part not only is slower, but it's kind of spiky. This is on purpose, it's not just casual. There is a feature of I2C, in the old days, I2C, let's remember that it's started 40 years ago. At that time, there was not really a specification, but a recommendation that has become a de facto spec that I2C devices should ignore any pulse that it's less than 15 nanoseconds. These are considered spikes. So in this case, the clock pulse, it's 40 nanosecond for 0 or less. And so this becomes invisible to I2C. So basically, in the first section, an I2C device just doesn't see the transaction. And then when it goes to faster mode, it just will not see it, basically. So that gives the compatibility at electrical level. So you see, this is very efficient because it's a way to probe the bus, only use the open drain for minimum necessary, and then go push-pull. So just to give you, flavor of what's happening there. Now, let's think about, we are used to, when we think about SPI or I2C, those buses are just moving bits from one device to another. But with I3C, we wanted to add more, there is more functions, management functions. So you can have a series of different kind of transactions. I'll try to show here the main ones. There is also some special cases, but I think gives a good coverage. So what I show in the first, let's say in the first line, It's what we call private read-write. So basically, after the probe, the broadcast probe that you do, you can do a repeated start. At this point, it behaves exactly like the I2C. So you want to read something from a target, you issue the address, you will get the acknowledge in OpenDrain. At this point, there is the I3C diverge from I2C in the sense that all the subsequent read, the acknowledge is not used anymore. We use what we call, it replaced with what we call the T-bit. T-bit is in push-pull, first of all, so it's faster. But it also has a different meaning if the sent by the controller or the target. So the controller is the parity of the data, and the target, it's really indication that there is no more data to send or more data to send. So the controller can keep on issuing the clock, to read more data or stop it. By doing repeated starts, for example, here you can read from a target, you write maybe on the same target or to a different target, some data, and so on. So it's similar to I2C, except, let's say, for the broadcast and the line modeling. We added, and this is where we really the two things diverge, what we called command codes, common command codes. This is a set of functions that are used to manage devices and manage the bus. They are issued right after the broadcast address and can do a number of functions. I give some example after, but think about, for example, we can define the maximum packet length. We don't want to hog the bus for too long. So we say, okay, no more than 128 bytes, for example. So with the command code, you enforce this. Of course, you need this to tell to which target. So after the command code, you will address the target to set something or to retrieve some parameters. So you can never read the right command codes. And further along, there is a possibility in I2C to have a broadcast messages. Broadcast messages are really of two kinds. One, you can address the full bus. Or sometimes it's useful, for example, to address only a subset of the bus. Let's say you want to disable or enable interrupts for 3 or 4 devices. So you can create a group, and then you with the broadcast address to the group, you manage only the group. Okay. So give you just a flavor of what these command codes are. It's there are about 57 command codes defined, but you don't have to implement it all. There is really 16 of them are really required to make a bus functional. The other are optional or conditioning on, depends on what you want to do. And they are about, in the table you see, managing bus events like enable, disable, interrupt. What to do when you generate, there is a pattern, it's called target reset. What should a target do when you receive this target reset? Do a full reset of only of the peripheral, and so on. The delay time, there's a whole number of parameters entering into some bus states, to in idle mode to save energy and so on. Quite a bit of command codes is actually reserved for what's called dynamic address managing. I have a slide. We have a slide after to explain a little more. But basically, in I3C, you are not hardwired with the manufacturer address, but like it's in I2C. In I2C, you buy a device, and the device has a fixed address, or maybe has 1 or 2 pins to manage, but it's basically hardwired. Here, it's dynamically assigned by the controller. There are the commands that Tim hinted before to enter the high-speed modes, multi-lane management, retrieve target capability for different functions, and so on. Probably it's very, this will be very long if you go in detail, but there is really a lot to it. I encourage to download the I3C Basic specification where you can actually find out what they do. So let me focus on the dynamic address now. How it is managed? Basically, is the controller doing this? It's a dynamic procedure where each target kind of presents itself with like a MAC ID, a 40-bit Unicode, and then the controller will assign an address. An address is 7 bits, so theoretically you have 127 addresses. In reality, there is a number of reserved addresses that are used by I2C. So the effective number of addresses is less, but it's probably way more than you would need. Because on a real bus, you probably won't have between 10 to 20 devices on the single bus. So having close to 100 devices is it's probably more than enough. Well, an interesting thing is that usually I will show you after why. If you have your address is lower in number, he has some kind of higher priority. So you can manage also the priority of the device by giving the addressing, assigning the code. There is also a way not to have the only dynamic address, but if you have a device that has a fixed hardwired address, the controller can just mark this as a virtual, as a fixed address inside its code internally. Okay. Another thing for helping to manage are the presence of some registers. We have 3 registers. One is basically explains the capability of a target, and this can be read with the common command code. There is a device register which basically identifies the device. You don't have to remember the part number and so on. You can query, and we have tables publicly available on MIPI side where you have all the currently defined code. This can be accelerometers. Somebody, a device target can identify itself as an accelerometer, a gas sensor, a security device, or whatever. And here there are the links of the currently defined device codes. Okay, now I will show maybe just a few examples of functions that you find no equal in the other buses. The first one is the in-band interrupt. Basically, this is a feature. This is one of the cases where the first byte, the broadcast address rule is not observed. Basically, a target can generate, can pull down the SDA line. The controller will clock it, and it will say the target will emit its own address. This flags that it's basically generating an interrupt, so the controller can acknowledge, and then not only so you have very fast, you don't need extra wires or other procedure. So you are notifying the controller that you're generating an interrupt, but attached to that, you can also put some extra data. So the first byte is what we call a mandatory data byte. Basically, it tells what kind of interrupt I'm generating. Is that an error, a data acquisition, or something? And for example, in the case of acquired data, we can also send the data along with the interrupt. So this gives a very fast, efficient way, not only to generate the interrupt, but also to pass the data in the same transactions. Here we're talking a few microseconds. So this is an example, after how fast you can do and transfer the data to the controller. Another interesting feature which is actually becomes very powerful where combined with IBI is the asynchronous timing. Basically, let's say you want to know exactly at what time an event happened. So you have 2 clocks, one in the controller, one in the target. So the target will start is a clock when the event happens. Let's say you're sampling a sensor value. Then you generate the interrupt. On the acknowledge rising edge, there is a first, let's say, you measure a second time the time, and then after the MDB, you do a second measurement, and then you sense the sensor data. By doing this calculation that you see on the 4th bullet point, actually the controller can know at very precise timing when the sensor sample was acquired. And we have the synchronous mode 0, it's a sub-microsecond precision. We have also more sophisticated, which is really maybe too complex to present here, where you can do all the way down to below 100 nanoseconds. So I think this opens the door for really some innovative, very performing applications. Here, by combining a scan, so you use the repeated start, you read a bunch of sensors, and then you use a command mode. This is enter bus status low speed. So this becomes you wake up, acquire the data, maybe with the synchronous mode, also with the very precise timing information, go to sleep. So it becomes, for repetitive type of data acquisition, it's very efficient in power and also in computing. And finally, I have the last example I would like to bring. This is, let's say you have a device that you don't need to be awake all the time, or you can physically join to the bus at a later time after the reset. This can be, in the example, a communication, wireless communication unit that you keep powered off, can be some other device. So in I3C, there is a possibility to join this in alive. The feature is called hot join. The way it's done, it's really a special it's a special interrupt with the predefined code. It's a 02, by the way. So because the unit that's joining does not have an address yet. So there is reserved this code that says, okay, there is somebody who's joined the bus and wants to become active. The thing is, so this makes it very useful. The thing is, if you put some unit to sleep, how do you wake it up? Say you want to maybe, and if we have an added signal, it just really, we don't want extra wires, right? That's the beauty of I3C. So what we have here, we have this hardware pattern. You will see that in the spec, there are similar patterns to this that are used for a number of functions that by wiggling the data line, it performs some hardware. So in this case, if you wiggle 14 times the SDA, this can generate a reset, wake up signal to the target. So it's very, no extra wires needed. You just use the bus protocol. Okay, just to summarize here, we say them in some slides ago. Tim showed that the basic. This is a summary of the functions, and you will see that the I3C Basic version 1.1 has 6. The one in red are not available, but if you see, there are really special features. I think for most of the designs, you can do it with I3C Basic. It's really not a great loss, not too heavy. It's mostly multi-lane and things which require really special hardware. And with that, I will let you go back the presentation to Tim. Thank you.
All right. Thank you, Michele. We'll just wrap it up real quick, kind of talk about the current state of MIPI, where we're at with the ecosystem. Right now we have a lot of documents out there in support of I3C. Starting from the left on the software side, we have the I3C HCI, which is the host controller interface, version 1.2. This is actually available on the mainstream Linux kernel, publicly available, and this facilitates the connection of peripheral devices to an application processor. We also have the TCRI, which is the transfer command and transfer interface. It defines the standard TNC structures and renders software reusable across applications there. As far as the kind of test side, we put together a conformance test suite. Basically, it focuses on SDR bus, but gives implementers a set of tests to run that can kind of help prove the correct implementation of their design. We also have a bunch of app notes and support, FAQ, all in order to help the implementer tackle some of the commonly known questions and some of the more difficult areas of the specification. As far as integration goes, I3C is out there. We've got the MIPI debug for I3C spec, which is within MIPI. There's the USB I3C device class, I3C over CSI2, PAL I3C, and then we're working with other industry groups as well. And then below here, I think this is another copy, some of our registers that Michele talked about with the DCR, the MDB. These are all implementers tables to help with those types of registers. I3C's working with other groups like JDEC, PCI SIG, ETSI. We're in the works with organizations like DMTF and IEEE. And from the product standpoint, you could see we're working all over the place, from microprocessors to sensors to DDR5 core memory. If anyone's familiar with memory, the SPD or sideband bus from JEDEC is built on top of I3C, and so we've had some great collaboration there with the JEDEC community, and then tons of different IPs available as well. So resources, there's tons of them available on the MIPI website. From my understanding, these slides are going to be made available to everyone, so we wanted to include all of these different links to bring you to the detailed information. And then upcoming opportunities. So MIPI is putting on an education week for I3Cs to explore in more detail the world of I3C. This will be next year, 2024, in February. So there's a link down there. Please check that out if you're interested in learning more. And then also, MIPI will be at Embedded World in Nuremberg, Germany. Also in 2024, April, we'll be doing presentations and conference there. So another opportunity to learn more about MIPI. How can you get involved? So I'm the chairman of the I3C working group. We meet every Wednesday at 8 a.m. Pacific time. You can also email the working group Reflector. We're very active and responsive to any questions that are received. And then if you want to get in touch with MIPI, there's some contacts as well there. Finally, just some acronyms to help as you're reviewing these slides or taking a second look to help understand what the different abbreviation. There's a lot of different terms, and so we want to make sure everyone knows what's going on. So that's it from us for today. Thank you, everybody, for coming in, and I hope you learned something new about I3C. Clemens, we'll pass it back to you.
Yes, thank you, Tim. Thank you, Michele. Also, that was very interesting. This is, of course, not the end of the webinar. This is just the end of the presentation. We will enter Q&A mode shortly. Before we do that, I do have two questions. That's the advantage of being the moderator. You have first right of question. You mentioned I3C can go up to 100 megabytes per second. Then do you address also a bus termination in the specification?
That, yeah, I think it was. They said 100 megabit, not megabits. Yeah.
So bus termination is not required at those speeds.
Yeah. There are recommendations. Yes. Okay. Yeah. Sorry. Go ahead. Yeah.
Yeah, the advantage of I3C is the fact that we can reach 100 megabits per second using the multi-lane configurations, not on a single data lane. So this means that effectively quadrupling the communication frequency of the single lane to reach the 100 megabits per second, but preserving the 12.5 megahertz clock speed. Okay. So we can reach these speeds, but using and taking advantage of the multi-lane configurations.
Okay, I see. And another question that came up for me, at least, you mentioned the dynamic addressing. If I understood it well, there are only 103 addresses possible. We have seen in the past that we always thought that 100 addresses or 64 bits or whatever is always enough, but after a few years, it's never enough. So why did you limit it to 100 and not immediately to 16-bit addresses or something?
Yeah, no, it's a 7-bit. Basically, this is a dynamic addressing, so it's only happening in that system and in a certain space and time. You know, it's not like that. Once you assign an address to the device, it stays there forever. So it's really a dynamic address. So we felt that this, you know, instead of adding an extra byte for others, I think it's just probably enough for a configuration to be alive in a certain moment and a certain time, because it, you know, it's not that if you assign an address to a device, that's blocked for the rest of the life. You know, the addresses are reused.
We can now answer I'll try to answer the questions from our audience. I will publish the first one. So 100 megabits per second. That's we already mentioned that. So that's true.
Yeah, 100 megabits per second would broken down into about 25 megabits per lane over the 4 lanes. So that's how we achieve the quad lane and the higher throughput.
We have a question. Can an I3C basic IP operate fully as I2C or as M-bus if customer wants to use the legacy IP, so I can avoid to support all 3 IPs on a single microcontroller? That's a long question.
Maybe this one requires a better explanation, because I've seen other questions raised also saying that when we say that I3C supports backward compatibility to I2C, we do not mean as a protocol, but the bus has provisions that allows it to add I2C devices on the bus and communicate with those I2C devices. It does not necessarily mean that those devices will be supporting the I2C protocol, but if there are I3C devices, and then if we would like to add an I2C device on the bus, then this is allowed by the protocol. So probably this one will provide a better clarification to the confusion, because by being backward compatible, it means that we provide a means of supporting I2C devices, not definitely meaning that these I3C devices will be I2C also. But that is up to the designer to support an I2C device. And I3C also, the specification also provides a provision that allows the I3C devices to work as I2C devices until they are assigned a dynamic address.
Yeah, I think at the end it really boils down to the IP designer. Some vendors, they integrate both cores, both I2C and I3C, and some keep it separate. So it's really on the selection of the IP to integrate in the product.
Okay. Here's another question about the backwards compatibility. Does backward compatibility to I2C have some limitations, or is it fully compatible?
Sure.
Wait.
There are. Continue, Michele.
Yeah. No, as you said, there are some features that. So, for instance, one of the key one is the spike filter, the 15 nanosecond, because which is actually kind of a de facto standard. Let's say it's not a standard; it's just more a recommendation. So, a lot of the I3C, I2C compatibility is based on the assumption that the I2C devices, they have the spike filter. So, and that allows, as we explained during the presentation, allows to do a number of things. So, and there are a few other options like this.
Yes. Not all I2C devices can be connected to an I3C bus. In addition to the spike filter, there are some addresses that are only reserved for I3C buses. And an I2C device with these reserved addresses is also not allowed on an I3C bus. This list of addresses can also be found. And with these 50 nanosecond also the spike filters, if devices do not have this spike filter, they should guarantee that they are able to tolerate the 12.5 megahertz communications and the clock speeds. And the biggest part would be no clock stretching is allowed. So if an I2C device stretches a clock, then it is not allowed to be on an I3C bus.
Perhaps I should mention that you've seen that we in I3C it's defined up to 3.3 volts, while it's common to see I2C on 5 volts. So this can be accommodated, but it's not part of the spec. It's really kind of stretching out a little bit. So this is another point to take into account.
Okay. Then there's some confusion about the SDA line. Is the same SDA transmitted on 2-lane or 4-lane SDA? I suppose not.
No, these are two options. In the multi-lane, you can have a ×2 multi-lane, so you have 2 SDA, and you can have a 4-lane where there are 4 SDA lines numbered, from 0 to 3. The way they behave, it's defined in the spec. They're not behaving the same. It's coding in depending on which HDR mode you're running to. So they send different signals. So you can have basically 2 options. If you want 3, one is single lane, single SDA. Then you have 2 SDA line or 4 SDA line.
There's an interesting question related to the same subject. In case of a 2-lane or 4-lane SDA, do all the hosts need to be 2-lane or 4-lane?
No,
if you have multi-host, of course.
The devices.
They don't need to be. This was designed in a way to support that the primary communication signaling that are start, repeated start, stop, the CCC commands are all done on the primary lane, that is a clock line and *0, which we call it the primary lane. Then the data is transmitted on the 2-lane or 4-lane. So some devices could be in dual lane and the others could be on quad lane communication. But the addressing and the initial parts are always done in a single lane communication. By using this method, we can mix all different kind of devices in all these different modes and use them in a single bus.
Then we have a totally different question. What actually means not in I3C Basic? Is it forbidden to use it without MIPI membership or forbidden to design chips using it, but available for system level designers?
I think the second one. Yeah, sorry, go ahead,
Yeah.
Tim.
No, you're right. Without getting too much into the whole legal side of things, it's the second. So as of right now, there are 2 separate specifications. There's the I3C full specification and the I3C basic specifications, 2 completely separate documents. And for the features that are not in I3C basic, they're not. The details are completely wiped from the spec, and there's just kind of the header for it, so there's no details there. And then the legal arrangement is such that it's meant to be for MIPI members only.
So it's for chip designers.
Yeah.
Next question. How can the transmission distance be determined knowing the transmission speed?
Okay. Transmission distance is indirectly controlled by the bus capacitance, because I3C is designed, or at least the provided frequency and timing parameters are within the spec are designed for a 50 picofarad bus, which is assuming about 5 picofarad per device, so up to 10 devices, and maybe with fewer devices, then the length of the bus can be stretched. But I've also seen that there was a request about 5-meter distance I3C, one that says so. This all depends on the signal integrity, propagation time, and all the other parameters. And inside the I3C, we say up to 12.5 megahertz, not necessarily 12.5. So based on, for example, a point-to-point system is able to communicate. But if there are multiple devices, then we have to consider the effective bus frequency and then use those parameters. So these have to be calculated based on the timing parameters that are provided and then scaling down to match the bus propagation time mostly, and bus loading also.
Complicated subject. If I3C transmits at the speed of 400K, the I2C devices on the bus will fail. Can the minimum speed for I3C be defined?
No, those devices will not fail. The only difference would be that, again, whenever there are I3C and I2C devices mixed on a bus, there is a speed called or a timing parameter that is defined as I3C mixed bus parameter, where the clock low period can be stretched, but the clock high period cannot exceed the 41 nanosecond time. This means that the 50 nanosecond anti-spike filter that is mandatory to be present for I2C devices will effectively filter out the clock high period. And by doing this, we are able to safely isolate the I2C devices from seeing an I3C communication.
Okay. Another I2C related question. So multi-master support in I2C is now specified as primary secondary controller mode in I3C.
Yeah, that's correct. So with one of the recent versions of I3C, we deprecated the terms of master and slave, which were classically used in I3C and I2C. And we have now included the more inclusive terms for controller and target. And so the multi-master is now the primary and secondary controller.
Okay, thank you. Next question. Are we able to use I2C controllers transmit with an I3C target? Message without header 7EX.
No.
No. That's
No.
a good answer. Is there an I3C version of a host adapter that can be purchased?
Some companies are, I don't know exactly what host adapter, but there are companies now offering microcontrollers and MCU. If you have MCU running Linux, you have the host control interface. For microcontrollers, they have even a company recently announced a dual I3C. And so I think we're just using the microcontroller, so not this will be a host adapter in this case.
Yes, I've seen data sheets of microcontrollers with I3C in it, so it is definitely existing. So with this protocol, the ability to reject noise is less than with I2C, or is
being push-pull most of the time, it's much more resilient to noise, I would say. I don't know, Yoel, if you want to.
Yes, I3C, one of the advantages of using I3C is the first thing is being high speed, we can transmit data in a short amount of time, which makes it less susceptible to more noise. The second one is being a communication that is in push-pull. It means that the possibility of having a noise depends on how strong your noise is, and having a stronger driver to send the data means that your signal would be more protected from noise. And in addition to that, I3C has also built-in parity bit control, usually for data communications from controller. And this also allows it to have a more noise control or noise-related communication errors.
Yeah. Perhaps if I could add, we didn't have time to go into this, but all the HDR modes and the burst transfer have the CRC included. So the data is packetized and protected by CRC. So only the SDR mode is a very basic parity check. But all the other modes, even burst transfer with the SDR mode has a CRC error detection that gives a very robust data transfer.
okay? We are nearing the end of the webinar. I suggest that we take one last question. I see an interesting question here, which is repeated. Is there an FPGA source code implementation of the controller and/or device?
I know that NXP released an open source on GitHub for a code. I don't know how complete it is, but I would assume yes, there are. Okay.
So you have to look for it if you want one, but it's not impossible, not forbidden, I suppose. Yeah, it's 5 o'clock, so we have to stop here. I would like to thank you very much for your presentation. It was really interesting, a lot of information. It was a bit quick, of course, but luckily, as I said at the beginning, this webinar is being recorded, and it will be available in a few days on the Elektor TV channel, so you can watch it again. We hope to see you again for the next Elektor webinar, which is next week already, on the 9th of November. And it will be about the marketing preferences of European engineers. So it's not a very technical subject. With that, I would like to say thank you very much to Tim, Michele, and AUL for doing this webinar with me. And thank you all for attending. And goodbye.
Thank you very much. Goodbye.
Bye-bye.
Thank you. Goodbye.
Bye.